Welcome to the lecture number 28. So in this lecture, we'll be talking about how you can be anonymous while in a peer-to-peer network. This also has been kind of a dream of people that they want to be on the internet, but nobody should be able to know who they are and where they are actually at any point of time. So we'll look into that. So far what we had done earlier was we had looked at identities. We have used identities earlier in all our discussions. So these identities were verified by sending an OTP. So normally we have taken identity as in email in our Brihaspati 4 platform which we have been building. We could have taken a phone number, mobile number, so where SMS could have been sent and we could have verified. So either phone number could have been used as a unique ID or email ID. B4 has been using email ID. And this actually then gets bound to node ID. So normally node IDs is what basically are used in any DST network for all kind of DST routing. And of course maintaining a network connectivity by using logarithmic partition. So, and of course when this user ID to node ID binding is done, so because node ID is a public key or being derived from public key, so there is a corresponding private key. It has to be signed by that. Okay. And of course this user ID node ID combination also has to be signed by the private key which is corresponding to the user ID. User ID is also, remember, is a public key. Is an email ID, and this email ID has been issued a public and private key, and public key is what is being used for verifications and private key is used for signatures. Okay, when this user ID is publishing the document. So this certificate which user ID has, basically user ID to the public private key pair mapping, is essentially signed by an authentication server in the which is done after verifying the OTP. Okay, that's the case which we have used. Now question is, can we go anonymous? Can I actually avoid using email ID and phone number and still form a peer-to-peer network? Surely you can do that actually. In that case, your node ID essentially is your public key and there is a corresponding private key with the node ID. Now only problem which remains is how that multiple users, a node can be on the multiple node ID, because each node ID will become a separate user as far as the system is concerned. Though it is possible, but it will be slightly tricky to implement. Okay, it's not impossible, but currently let's assume that it's going to be every node is unique. In that case, what happens? Okay, now the question is why we would like to go anonymous. Okay, why not to actually show your identity? Sometimes what happens is, this has been seen around the world, there are oppressive regimes in certain countries. So people who want to communicate, they don't want to come into limelight of the oppressive regimes, otherwise they will be eliminated, basically killed. So when you want to build up a revolt around that time, so this we have seen is happening in Hong Kong. People have used such systems, anonymous systems. They have been used by Edward Snowden. They have been used to build darknet kind of structure, but that's, I think, slightly more. We will delve into the Tor kind of system later, which is extremely anonymous, and this is one reason why they might be of interest. Then there is always, most of the countries or any government or any leader or any dictator will be always having intelligence gathering mechanisms. So he will be hiring a lot of people. Almost all government does, and I think there are a lot of I think popular intelligence agencies. So we have seen James Bond movies, so MI6, everybody knows about them. So that's a British intelligence agency. We have RAW, which is Indian intelligence, ISI Pakistan, we have Mossad, which is from Israel, and so on, CIA, KGB, and then of course similarly there is Chinese agency also, almost every country invariably. So that's now when they actually gather this information, okay, so what has to be done in that case? So normally is of course unsaid, but this is true that almost everybody plants spies everywhere to collect information, and whenever they are caught, normally the hostile countries will normally kill them. or they will be eliminated without telling anybody. So it's a very risky business, but people do get involved for the sake of their country. They call it sacrifice to the country. So when they do it, so technology also has been built. So this actually being anonymous also becomes useful in those scenarios. Okay. So, and because they need to communicate back to their own country without getting into the hands of the enemy. So in the country where they have been planted. So this could be one possible way. In fact, the Tor came out probably from one such effort. I'm actually not sure, but my guess is yes, probably most likely it's that. There can be other also good uses, like good governments can use it to collect information from whistleblowers without endangering their life, and of course then improving governance on that basis by eliminating all the corrupt people who are not good for the social life or for the whole country. Okay, so there is also within an organization, if two entities are communicating and they don't want anybody to know who is talking to whom. Okay, so nobody should be able to trace if these two people are talking, but they actually are talking. Okay, so not only what they are communicating, and even that they should know that they are even communicating, that also should not become evident. So not only what they are communicating. Okay, so in those scenarios also, this kind of systems become pretty handy. And they actually evolved over time because of for that reason, and a lot of them are available in open source. So I have been mostly gained my know-how from the open source community. So for example, A to B, if I want to communicate, what I will do, I will actually now create a secure tunnel from A to B. So basically create an encrypted thing. So it goes through routers, the encrypted packet. Routers can't decipher. Only A and B has the keys, so they know it. But now the problem is routers will know that A is communicating to B whenever it is happening. That itself is the information. So that can decipher, okay, at from what time to what time A and B are communicating. That itself is the information. Even that need to be hidden. And of course, for a spy this becomes complicated because if they are communicating somebody from a hostile country back to his own country, and the timing is known, if we know even the IP address, what they are communicating is not known, so there is no evidence. Okay, but when you do all unethical things, there is nothing like evidence. You just do it that time. So they can find out the IP address, they can locate the guy. So we cannot use it actually. Okay, and of course, if you know the other one endpoint is you cannot rely on, the other endpoint also you cannot rely on. So you can actually make these connections, and then statistically you can figure out who are the culprits and then take care of them. So this is a pretty common practice. So anonymity becomes extremely important in those scenarios. Now normally the problem here is what will identify A? It's the IP address. And from IP address you can always get the location. There is no user ID. Okay. So you can simply do with verified identities, email ID and phone numbers, because then it becomes even simpler. So those you can throw away. Okay. But IP address can still be done. So it's actually not completely anonymous, but still, yes, the systems are there. So I will talk about one of such system now. So this is A can generate a random node ID, for example. So his IP address will be known, but this can be taken care of by actually routing. So we will be doing that. I will be explaining how it is done. So A can generate a random node ID. It will be basically generating a public key and private key pair. And from public key it will generate a node ID. So node ID and public key together is essentially the node ID. And of course, if you know the public key, you can't find the private key. And the whole system now hinges on this. Okay, and this is true when these keys are pretty large in RSA. Okay, and this is a Revesz-Shamir-Edelman algorithm, RSA algorithm, which is used normally. It's pretty much safe, used for a lot of commercial transactions. It's called public key cryptographic infrastructure actually. But there, this basically depends on certificates. Here there is no certificates actually. So now what we can do is, when these guys are communicating, they should know each other's public keys, they should be sure it's actually got to the same guy, and they can now use symmetric key for doing all communication. And as we have done in one of the earlier lectures, symmetric keys can be generated through SSL, basically generating a random number, encrypting with the public key of the other guy, okay, and then of course sending it in an encrypted fashion. The other guy can get that. He will generate his own random ID, and whatever is a decrypted random ID, a random node, the random number, both numbers, it will actually then decrypt in the reverse encrypt in the reverse direction using the public key of A. It will come back to public key A, and A will get its own random number back. If it matches, so B is genuine. He does have a private key corresponding to the public key. Now A's turn to prove that he has the private key. So because he has decrypted B's random number, it will send it back again using public key of the B, and B will decrypt it, and B knows, yes, I got from A the correct random number, so A is also genuine. They will now both combine these two random numbers and generate a symmetric key. So this is not known to anybody, and this can be used for communication. They now can do something more. This is what exactly is done in some of the products. Intuitively I can guess that, and that's why it's very tough to actually crack them. So they actually change the symmetric key pretty fast. Every few minutes or even every 5 minutes, if it is done, it's very difficult to crack, because by the time you crack, the key would have changed. The eavesdropper will never get a time to find the symmetric key, and if it's long enough, and you're changing it pretty fast periodically. Okay, so you essentially has to ensure that the periodicity has to be good enough so that the time to crack the symmetric key is much larger than the period, and this happens with very high probability. So the guy most likely will never be able to crack, and you can keep on communicating secretly. But only problem is the location can be identified. So one of the actually applications, which is ToxChat, this is available on open source. It is available. The whole code is on GitHub, and there is Android app also, which is available but not very popular. There is no ad, there is nothing. It does not use any server. That's one of the beautiful things. And it does messaging with that. Now the messaging here becomes slightly different. Earlier when we talked about messaging, we had a messaging storage, mail storage we have talked about. Okay, so mail storage, essentially that's what the messaging is. But it becomes slightly different. I used mail storage because the mail was sent between user IDs, not between the node IDs. Okay, when I send it using between node IDs, I don't actually require storage. The routers itself act like a storage because the message is going through DHT route. Okay. Now public key is the user ID in this case, and of course there is no anonymity, as I mentioned, so one can find the IP address of the entity and hence its location. So this is actually not anonymous in that sense. Of course, a common man has to first of all get the IP address of the other side, but since it's going through multiple hops, unless you know everybody in the hop, you will not be able to figure out what are the IP address. Okay, so and this can be even made more secure. Tor is essentially based on that. But Ntox is a pretty simple application, but very effective. You can download from Play Store. It's available for free, and then of course try it out. But you won't be getting name of your friend. Your friend has to tell his public ID to you, which you then have to load into your Ntox chat, and then you can communicate with him. And you have to tell his public ID. That's how he will recognize you. Then you can actually put some name aliases in your mailboxes in Ntox chat, and then communicate with each other. There are no names, there are only public IDs. Public keys are known to both sides. So your address book essentially is for each, you have to put your aliases or names, but you only remember for all users, you will recognize by alias, but it's the public IDs of all users which you will be listing in your address book. So blockchain also uses very similar thing. It does not use any user ID, it uses public key, which is basically becomes a user ID. So any bitcoins or any smart contracts are assigned to the public key. So if you hold the private key, you hold those particular bitcoins. If you lose your private key, you lose everything actually. So far you know your private key, you exist. You forget your private key, everything is lost. Unless somebody else by chance gets the same private key while doing random generation, which is very, very far-fetched, extremely improbable event. So it's going to be lost. It has happened with people. They have lost a large amount of bitcoins, which if would have been accessible, would have been a huge thing. People's hard disk have crashed, or hard disk has gone into water, they could never recover it. They have lost huge amount of money. So if you search the internet, you can find such cases. So normally important thing is that with NTOX, there will be always a bootstrap node which is programmed. So there is at least one node which is running, which is known to everybody. This comes hard coded. So when the system runs, it puts in its routing table only one entry by default, which is the bootstrap node. Since it is there, it starts doing routing table action. So it communicates to bootstrap node, and bootstrap node will send its own routing table back to you, and you will start populating it. Now you communicate to all these nodes, they will send their routing tables, you will keep on optimizing. Okay, you will start creating logarithmic partitioning. Kademlia is a pretty popular thing. I think that's what also has been used in ToxChat. I have not actually verified this, but that's my intuition because almost everybody has done that. But in Brihaspati 4, we have been using a different one, it's a Quad Tapestry hybrid. But we are using assigning user IDs. We have not still built an anonymous system. We have not done that. Maybe in future we will see if it is required. Okay. And then of course there is a logarithmic partitioning, so network will always remain connected, as I had talked about in one of the earlier lectures. You can also maintain neighbor table, but it's an optional. But if you do it, you can actually make the whole network routing far more efficient, and I think it's desirable we should do that. Now the question is, if user has two devices, there will be two different users, because users are identified by public key, which gives the node IDs. So it cannot be same user. Okay. And of course, we can do one more thing. We can actually use, for same node ID, multiple endpoint address can be given. Okay, so in that case, the problem is when you are participating, you cannot participate in DHT. You have to register in DHT and you have two endpoint address. You are node ID, but you are not part of DHT. Okay, so it will come to your root node, and from there it can be then sent to one of the two. But if you are participating in DHT, you have to be only one node. You can't be two, because two nodes cannot be placed at the same place, two different devices. Okay, it will become pretty much confusing. So routing tables will have only, for each node ID there is going to be only one endpoint address entry, not two. Routing tables don't do that. Okay, so only as a special case when they are leaf node it is possible. As I told, it's not impossible, it can be done. It is possible to create alias. Okay, there can be two different node IDs, and both of them we can actually have a signed information that they are alias to each other. They are actually same user for each other. So in that case, when you send it to one, it automatically knows that the other person I can inform. So it can now encapsulate the message and send it to the other node ID also. So both can keep on synchronizing essentially between them. That can be done, but currently B4 we are not at all investigating this particular thing. And now when these devices, there are two devices, do multiple endpoint addresses for same node ID case. So when they leaf node, they need to, both of them need to have the private key for the same node ID. Otherwise it's not going to work. Okay, they can't otherwise verify the things, so they can't do a transaction with any other node. So how the ToxChat is going to work? Let's see. So now let the user A wants to talk to user B. So user A has a node ID A. So I call it node A here. So now the problem is somehow A should know what is the public key of the B or node ID of B, and B should know what's the node ID of A. Otherwise they can't communicate. So maybe when they have met in somewhere in the conference, they have exchanged their node IDs. So that's what happens through an alternate channel in ToxChat or in NTOX. These public keys have to be exchanged, and you have to put them in your TOX client or NTOX client. Okay. So once this is done, what A will do is A will now send a endpoint address query to the B's node ID, and it will be done through a DHT routing. So ultimately query will reach to B. So this is what is being shown here with the red color. So this actually query goes to B. Okay, so now B will respond to A. B may respond only if A's public key is listed in the friend list. That's what happens in the ToxChat. If it's not there, it won't be actually doing that. Okay, you have to accept it as a friend, then you can do it. So B will now also check whether it's actually saying that A's node ID is this, whether it is being signed by private key or not. Somebody should not be faking. So if it is signed by the corresponding private key, B just verifies yes, it's actually coming from the guy who claims his node ID is this, because signed by the corresponding private key, which can be verified. So B will send the message back to A in the same fashion, so A can verify it is indeed coming from B. So A by this time knows what's the endpoint address of B. Okay. And of course, A and B now can communicate through IP routing, and they can set up a secure link after mutual verification, and they can transact. They can make a voice call. That's how the NTOX actually is doing voice call from between two nodes. So there is a peer-to-peer call directly, but set up without a server. Okay, and they can make it encrypted, and it is actually encrypted, and the key can be modified every 5 minutes, say. So 5 minutes is a pretty small time. By the time you know the traffic, do the traffic analysis and find out the key, symmetric key, the key would have changed. So there is going to be essentially what happens, you are working with the older key, at that same time you do further another mutual verification and set up a new session key. So basically two new random numbers being exchanged, and then you signal to the switch over to the new key to each other and just flip over the other key, and the communication actually changes to the new key. So that's how the key management protocol actually keeps on happening. When you want to create group messaging or group calls, they have to be direct point to point. There is nothing like a list server equivalent will not be there, or there will not be any what we call a bridge for the calls. It has to be directly point to point. So in such a system, because this is basically built for secrecy, so it remains simple. That's the way it is done. So normally you do one point to point call, and that guy will relay the information to the next guy. You do it one by one. Okay. So that's the way. Or you, from your same device, you actually start generating multiple copies and to the people. And normally such systems are going to be for very small groups, not for very large ones. So the security is going to be reduced drastically as the number of people in the group actually grows. So that's the rule. So the moment you talk about security, number of people in the group normally will be very small. Okay. So TOX does allow messaging. Basically, it's like chat. It does allow voice over IP, and you need to know the other person's public key. That's very important. So all nodes can store the messages for other nodes temporarily for some duration. So that is permitted. So it's not like a message store. This happens while the message is going through DHT routing itself. Now if the other guy is off, destination is off, the intermediate node will not be having that guy in his routing table. The message will just keep on lying there because it's a root node for that destination. But only thing, the guy who is a destination, when it becomes alive, he becomes his own root node, message will get transferred, and then he can decipher it. Nobody in between can do it. You always encrypt the message with a symmetric key, and that symmetric key is further actually encrypted with the public key of the destination if the message is very large. If it's short, you can directly encrypt with the public key. Only the destination can unlock this whole message and can actually read through it. So in this case, as I told, that root of B, say node C will hold the message as root B does not exist. Whenever B will come alive, routing table of C will change and the message will move to B. There is some other better root node for the same message now is going to be there. So there has to be an entry change, routing table change has to happen. This we have discussed earlier also. And we don't require a separate storage layer. Now maybe you can question that we could have used this thing in peer-to-peer mailing system also. No, there you can't. Okay, so when forwarding a message to a destination B, nobody except B should handle it. That was basically the idea. Okay, and we have done this thing here, and there also it is done. It's encrypted. You keep the message in temporary storage. When B will come alive, an RT table will change and message will go to B. B is the only root of itself. That's what I have told for this particular system. But in peer-to-peer, we are actually sending message not to the node ID but to the user ID. And it can be on multiple devices registered. So any one of the devices which are live will pick up the message and will then put it into a DFS storage which is shared across all the nodes. So that's how actually every device will get the message. But any device can pull up the message from the message store. We don't have that requirement here. And of course, if B is a leaf node, the message will reach in the root node, which is going to be C. And C will have to keep the endpoint address of B, and whenever B will come alive, C will pass it the message to it actually. That's the way it is going to be implemented in case of NTOX or TalkChat. But TalkChat, every node is participating in DHT. And this actually means when you are sending DHT messages, even intermediate nodes, you can actually transmit large size messages with attachment. Okay. But again, in peer-to-peer mail systems, because attachments can be very large, so we have assumed that if both nodes are alive, they will directly do a transaction point to point through an IP connection. They will essentially set up a TCP or a UDP connection and transfer the whole message in one go, whatever be the attachment size. Otherwise, they have to use message storage, so storage size has to be larger for large attachment. But it's for a very temporary period till B comes alive and picks up the attachment and messages both. In this case, probably that is going to be difficult. In fact, TalkChat does not allow a large attachments as of now. Okay, you can only send short messages. I have not actually tested this system very thoroughly. Okay, and of course, all the messages will get delivered to the node ID in this scenario. And with separate verifiable user ID, you require a message storage, as I mentioned earlier. And so TalkChat does not require message storage, and message has to be stored at the previous node for resilience. So now there is a problem of resilience actually can come. We can think there is a problem if the node which is holding, because B was off, that node itself dies off. For example, A to B to C to, and then it goes to the last guy. And if C dies off, the message was here, the message is lost. There is no way. So maybe one possibility is that a previous guy can also hold the message. So we can actually now do this thing that A transmits a message to B. B is not the destination, but it keeps the message with itself. When B has forwarded the message to the next guy, C will say confirmation that I have received it. When this guy gets a confirmation, it will say confirmation for the forward, successful forward. So A can remove the message. So there will be always two copies in the pipeline. When C will transfer it to the destination and it gives a confirmation it has received, C can inform him and he can remove the message. And see, when C has got confirmation and it is a destination, it can also remove the message has been delivered. So there is a twin duplication which actually can be done for resilience purpose, but there is a better way of also doing it. So let's explain how this will be done. So in the case of the same procedure which has been identified with 1 and 2, so A sends this one, A sends to B, and B both will maintain copy. B will send to C, A will get the confirmation of the forward, it will remove, B will get the confirmation of receipt, and A will remove it from the cache. So only two copies. And B and C will periodically keep on attempting to send it to the destination. If C fails, B will route it to some other node, which is now going to the next hop towards the destination, and through that route now it will be passing through. Okay. And if B fails, it does not matter, C is still making an attempt and it's not there, and some other becomes a better route node, it will try there. But if B fails and then comes back again, you are only depending on C. If C fails, it's gone actually. You can't do much in this such a small system, but which is okay, you have improved reliability to an extent. Another way to solve this particular problem is, as I am mentioning, both B and C, if they both die, of course message is lost. You have improved reliability, but you are not 100% sure that message will exist. So one way to solve the problem is that you create intermediaries actually. So from source, when you want to send a message to destination, you now generate a copy one for the destination. So don't send it to destination directly. Send it to an intermediary which is going to be identified by destination. Append the message copy one, a string to this, compute the hash, and whoever is the root of that become intermediary one. Send the message to him. This guy will now do the copy 2 to the destination. Create intermediary 2. So this 2 now will start backing up each other. If this guy dies off, this will create another copy. This guy dies off, another node will take over. So there is always 2 nodes doing it. Now this guy now sends the message to destination. And if there is a timeout, the destination has to now confirm back to him that I have got the message, so this can then release itself actually. Okay, so this can release that particular message. Remember, for this destination, this will always remain intermediary, so all messages will be routed through this way. But this intermediary always exists, they will never be dying off. And there is no message store. This is basically a DST routing. So first of all, you route it here and you are tunneling it actually. And from there, then it goes to the destination. So it remains there in the DST mechanism. So whenever the routing table says, it will keep on doing it, but it will just keep it here till you get a confirmation from the destination. So that's the only change which is going to happen in this intermediary. We have to make some changes for the tunneling thing. That's what has been done in the talks chat. So it's extremely reliable in message delivery for these reasons. Okay, and this causes the message to reach. Now I1 need to put a unique sequence number to each forwarded message. So why this is required is destination need to use it to reference when sending back the confirmation receipt to the intermediary. Okay, and whenever I1 gets a confirmation, it passes to intermediary 2. So both the temporary copies will be removed from both the nodes actually. And this system will keep on working beautifully, providing resilience. Now there is a slightly different design now, but it was there because we were not having any user ID. It was based on node IDs actually. So with that we close this lecture, and we will look into something interesting in the next lecture, which will be about how the blockchain actually works, which is also another peer-to-peer system. There is nothing as such for peer-to-peer there, but still it's an interesting topic, so I will just explain that thing, because it is also based on, it's built on top of peer-to-peer system. Thank you.